learning, and we are saving the best for last, the ratio test. So the ratio test is probably one of the tests that we will use the most often for the second half of chapter 8. So the 8.7 through 8.10, we'll use ratio test quite a bit. So we'll be looking at our infinite series, and we want to make sure that there are non-zero terms. And even if there were zero terms, we would just scooch the index along to make it be that maybe if the first term or two were 0, right, then it would be, started at 1 instead of, or started at 3 instead of 1. Okay, so, and then the in-terms approach 0, remember, so that's different, right? The in-terms approach 0. Okay, so what does the ratio test say? So the ratio test says that we will have a series that converges absolutely. So despite it being alternating or not alternating, if this ratio is true and it is less than 1, then our series would converge absolutely. So just to keep in mind, so AN is just the original sequence that we have. And then AN plus 1 is the next term of the original sequence. And it is found by replacing in with n plus 1. And occasionally what might happen is you might be given like the nth plus 1, and then you can actually find the nth term instead. But when you write your ratio, you do need to make sure that you get your ratio in the correct order, that you have like your larger term over your smaller term. So the nth plus 1 term over the nth term. And if that ratio is less than 1, then your series is supposed to converge absolutely. And that's because we are using the absolute value bars. And then if that ratio happens to be greater than 1, so if the ratio is greater than 1, then our series would diverge. And then greater than 1 would also include if it goes to infinity. Okay, here's the make some sad faces here, that the ratio test is inconclusive if the rate of growth is too close. So if that rate of growth is equal to 1, then it is inconclusive, and then we have to try another test. So if you're using the ratio test and you get equal to 1, and then you write your answer as inconclusive, and then end of story, then you get it wrong, because that just means you use a test that didn't work, and you didn't investigate further, does it converge or diverge? So if you get a ratio equal to 1, then you need to try another test. And that just means that your terms are too close together to determine, like there isn't a steep enough growth to determine whether or not it will converge or diverge, whichever way it goes. Okay, so let's go ahead and take a look at our first example here. So we're going to be using ratio test for this one. And so for our steps, so we will write, I will write my steps over here off to the side, is I always want to go ahead and write out like what is my AN. So write out AN, which is just whatever the sequence is, so the rule, right? So write out your AN. And so that is just the piece that follows the sigma, right, which is the rule for the sequence. So I know this is an infinite series, but I'm just writing out like what those different values are, okay? So A sub n is 2 to the n over n squared. And then my second step, once I do that, is I want to replace n with n plus 1. And I'm going to do a little bit of simplifying as well. And that is to find what we call the nth plus 1 term, or a subscript n plus 1, okay? And then do simplify a bit. And then you can do that like in, the next step as well. But that's just to kind of help you out with, eventually you're going to have to do some simplifying. Okay, so I'm going to find the nth plus 1 term. And so wherever I see an n, I'm going to replace it with n plus 1, making sure I keep my groupings correct. So this would be 2 to the power of n plus 1, and then this would be n plus 1, and then quantity squared. Okay, always making sure you're paying attention to your groupings. And then once you do that, you're going to go ahead and set up your ratio. or the limit of the ratio, I should say. And so for that, that is where, again, we're looking at, what is the limit as n approaches infinity of a sub n plus 1 over a sub n. So this is what we're trying to determine. Is that less than 1? Is it greater than 1? And then hopefully it doesn't equal 1, because then that means, boo, I got to do something else, okay? All right, so let's go ahead and set that up. And it's going to be the absolute value. So it's the a sub n plus 1, so that would be this one right here. And then n plus 1 squared, so it does, so simplify a bit. So I'm going to go ahead and distribute that out in this line right here. So that would be n squared plus 1n plus itself, and then plus 1. And then we would divide by an, but instead of dividing by an, I'm going to multiply by the reciprocal, because I'm always going to have kind of a fraction form. And so instead of doing a complex fraction, I'm going to multiply by the reciprocal. Okay. So then I'm going to write that here. So instead of doing, divide by the fraction, I'm going to just multiply by the reciprocal, and that is just to save me a step. So I'm going to write just recip. Okay. All right. So then once I do that, then my next step is going to be to simplify and evaluate the limit. Okay, so you don't need to do this, but I do just so I can talk about it, is I put my fractions together based upon like what portion that they were in line with. So like, for example, so this is the 2 to the n piece. I'm going to write that over 2 to the n. So I'm just going to scramble kind of the fraction, like that will be how I always will simplify when I talk about it and explain it. So I'm just rearranging, this out, so I'm going to multiply them, right? So, but I'm going to put them in the correct order. So then once I get to here, then, oops, I hit the wrong button. Then the next thing is now my n squared. I'm going to put over my n squared term. So all I'm doing is just kind of rearranging my fraction so that when I look at this, I can see, okay, what piece belongs to what's going to simplify with what. Like that's really just kind of my goal there. So I'm putting my kind of geometric look together and then my polynomial look together so that now I can simplify. So for simplifying this, so whenever I am dividing, I subtract my powers. So I'm going to go ahead and subtract my powers here. So n plus 1 minus n would just be 1. So that would be 2 to the first. And then this won't reduce at all, right? So that does not reduce. So that was going to stay n squared and then over n squared plus 2n plus 1, right? So then one more step here. And now keep in mind some of this, like all this writing of these steps, you can certainly do, all in one step. I just like to write it out just so I can see what I'm doing a little bit easier. And then I'm going to put a 1 right here. And this is still an absolute value. So what did I do? Just to remind, right? So if I have 2 to the n plus 1 over 2 to the n, I just subtracted those powers. So that would be n plus 1 and then minus n. And then that's how I got that 2 to the first. And then the n squared didn't do anything. It's just there. And then my n squared denominator is there. Okay, so then now when I take the limit to the infinity here, I see that I have both have a degree of 2. So then I just take the coefficients. And so then that limit would be 2 over 1, which is 2. And so then my final step is, to make a conclusion, so make your conclusion based upon what the rule says, right? So what does the rule say? So it's about 1, right? So I know that 2 is greater than 1. So 2 is greater than 1. So if I look up here, I know then that my series would diverge. And so that means the ratio of the next term to the previous term is double. So it's always doubling. So that means each term is getting larger and larger. And so then I know that my infinite series then will diverge. Okay. So another way to look at that is I know that if I were to go back to kind of that original problem, like this one right here that I have, I can see that 2 to the n is exponential versus n squared, which is a polynomial. And exponentials is one of our fastest growing functions. And so because of that, the numerator is growing faster than the denominator. So like as far as intuition goes, like it's not a shock that I got a diverging series. Okay. Now that is not justification to say, oh, the exponential's in the numerator, it's growing faster, therefore it diverges. That is not a justification. That's just kind of developing your intuition. Okay. All right. So let's go ahead and take a look at the second example, which is our last one. So I'm going to go ahead and write out my an. So that is n factorial squared, and then 3n factorial. And then to find the nth plus 1, I'm going to go ahead and replace n with n plus 1 and paying attention to my groupings. Right? So all I'm doing is taking the n, replacing it with n plus 1, and then the same here. So this is 3, and then group it, replace n with n plus 1, group it, and then that is a factorial. All right, so let's write out our limit. And then when I do write out my limit, I am going to do a little bit of simplifying at the same time. So we're going to do the nth plus 1. So n plus 1 factorial squared. So that means I have 2 of those. So I'm going to write it out twice instead of having it as a squared. And then divided by, and then I'm going to distribute the 3, right? So I'm just doing a little bit of simplifying, not a lot. As we go. And then instead of dividing by an, I'm going to multiply by the reciprocal. So then that would be 3n factorial, and then over, and then n factorial squared. So write it out twice. Okay, so then now I'm going to do my whole like rearranged a little bit. Okay, so I'm going to put all my 3 n's, I'm going to put those together. So I'm going to align those. And again, this is not a step I have to do. This is just one that helps me kind of see things better. So I'm going to do 3n factorial. And then I'm going to put that in the numerator of like the 3n plus 3, like put those in line. And then that way when I see, okay, how do I simplify the factorials? Like I'll know like, you know, which goes with which. Okay, so then times, and then I have my n plus 1 factorials. And then my n factorials. Okay. All right. And then from there, I'm going to go ahead and reduce my factorials. So I want to take the larger termed one and count down. So this is my larger one. So I'm going to count down. And then these are my larger ones. So I'm going to count those down. So let me do that right here. So the 3n factorial will stay the same, but I'm going to count down to get to that, right? So I have 3n plus 3, and then 1 less would be 3n plus 2, 1 less would be 3n plus 1, 1 less would be 3n, and then dot, dot, dot. So now those are matching, so we're good. So then now I'm going to times. So this section is done. And then now I'm going to count down both of my n plus 1s. So I have n plus 1 times 1 less, which is n factorial. Right? So that means these will be lined up, and then do it again. So count this one down and then stop when you get to here. So n plus 1, 1 less is n, and then so on, and so on will be the factorial. And then now in factorials, I'll keep the same because those are the smaller ones. So I'm writing kind of giant here. So let me scoot. Hold on, let me okay, so let me try this again one more time. There we go. Just give myself a little bit of room. Okay, so then now when I go to reduce all of this, I can see that the 3n factorials cancel, the n factorials cancel. And so then what am I left with? In the numerator, I have n plus 1 times itself. And then over 3n plus 3, 3n plus 2, and 3n plus 1. Okay, so when I look at this right here, I can see that in the numerator, so I would have n plus 1 times itself. So that would be, some sort of like n squared term, right? And then down here, I would have 3n times itself. So that would be some sort of 27n cubed distributed out. So then this is, do you remember like bottom heavy, top heavy? So this is bottom heavy because it has a higher power. So I could like add a 0 n cubed over here, but if it was bottom heavy, then it would be like there is no n cubed, right? So 0 over 27. So this whole thing would be equal to 0, which is a value smaller than 1. And so if it's a value smaller than 1, then that conclusion is that our series converges absolutely. And that is it.